Marc is our newest principal developer. He is now at Colorado State here in Colorado at the same university as me. He has for several years already worked really, really hard on implementing HP method in parallel context. So until recently, until 2 years ago or so, HP methods did not work in the parallel context. And he has implemented basically everything that is necessary for this. And I think that's what he's going to talk about today. So Marc, take it from here.
Yeah, well, thank you, Wolfgang, for the introduction. Yeah, I want to present the current progress on HP-adaptive FEM in context of parallel parallelization with this talk. And in particular, I want to talk about what HP-adaptive FEM actually is and what you need to consider if you want to use it in a parallel context, which are efficient solvers, like in a multi-grid approach, and that you also can use MatrixFree methods in that regard. So this is like a brief overview of what I'm going to do. So first, what is hp-FEM and how do you use it in deal.II? And then I will point out the challenges that you need to consider if you want to use it in a parallel context. And then in the end, we have a new tutorial step, which is step 75. And I'll just briefly introduce what this tutorial is about, and we'll look at some nice results in the end. So what is HP-adaptive FEM? I mean, most of you are using deal.II are familiar with why you're using adaptive mesh refinement, for example. So you want to align this discretization resolution with the complexity of your current solution. And the FEM method allows us to do that in 2 different ways. One's with age adaptation, where you can assign the size of your cells dynamically to your solution, which is particularly good if your solution is irregular, which means that it either has singularities or like jumps in the solution. Or you can use p-adaptation, and that means that you can assign like different finite elements to certain cells and basically have different function spaces assigned to each cell. For example, if you have Lagrange elements, you assign different polynomial degrees to each cell, hence the name p-adaptation, p for polynomial degree. And this is particularly good for smooth solutions that are easily representable by polynomials. And the combination of both is possible, hence the name HP-adaptive. And an example is shown here in the right illustration. So the top half of the mesh is age-refined, so you have an age-refined cell. And the bottom cell is represented by a higher order finite element. So the little dots here represent nodes on that cell. So in particular, this should represent a Q3 cell, for example. So you can mix both approaches with that. So why do you do all of this HP-adaptive stuff? So with age adaptation alone, you can only gain algebraic convergence, so like linear quadratic convergence. But with HP-adaptation, you are in theory able to have exponential convergence of your solution, which is why we are dealing with that topic here. And so to give you a brief history about the HP implementation in deal.II, I thought this would be interesting also for the other principal developers here, to give you an overview about the implementation history in deal.II. So the basic functionality of HP adaptivity has been introduced in 2007 with the 6.0 release, and a demonstration has been provided with the step 27 tutorial. And in the course over the next years, FE-nothing elements in step 46 has been added to deal.II, which allow to use the HP framework for multiphysics applications. And then with the 8.5 release, basically step 27 has been reworked and simplified. So that functionality has been carried out to the FE series namespace, which basically take care of transferring the solution to a Fourier series if you know what step 27 is about, we use this kind of Fourier series to determine the smoothness of the solution. So yeah, the step 27 has been simplified in that release. Starting with release 9.0, we've been working on making the HP framework possible with to be used in the parallel context. So since release 9.0, we have support for shared triangulations, and since release 9.1, you can use the hp-FEM with distributed triangulations, and I'm pretty sure you can also use it for fully distributed triangulations at that stage. But and since release 9.2 basically overhauled the HP framework, and to make it just easier to use, I mean, easier to use in the sense of as easy to use as the current grid refinement framework. So yeah, we introduced functions in the HP refinement framework that you can use to easily decide if you want to use H or P refinement in special cases, and we introduce future F indices, but I will talk about that in the next slide. And with the current release, we introduced the new tutorial step 75, which shows you how to use parallel hp-FEM on a simple Poisson example. And you can also use global coarsening, which we also present in this particular tutorial for your efficient solver, or like in the multi-grid context. But Peter already talked about that in the and Peter and Martin already talked about this in the previous presentation. So how can you use HP in deal.II? So what you basically need to do is you need to provide an hp-FE collection object, which is a collection of different finite element objects, and you need to register that with your DOF handler object by calling distribute DOFs. And then you assign using active FE indices, you assign different finite elements to certain cells. So each cell has an active FE index, which points to the position in your FE collection. So that's how you basically use HP, an HP distribution of your mesh. Just as a side note, deal.II veterans will know that there was a class HP DOF handler. This is no longer required to use. You can use the normal DOF handler, and actually the HP DOF handler doesn't exist anymore. It's just an alias for the original DOF handler class. So if you want to use dynamic HP adaptation, so if you want to change a finite element over consecutive refinements, I would encourage you to use the future FE index in that sense, which basically you can assign a future FE index on each cell, which tells it what finite element will be assigned to it after you perform refinement. So this is like the equivalent of refine flags and coarsen flags in the context of grid refinement. Yeah. And if you want to do that automatically, you can use functions of the HP refinement namespace that offer you decision strategies. So if you want to apply H refinement or P refinement to a certain cell. So this is the equivalent of the grid refinement namespace that you can use for H adaptation alone. And depending on which strategy you want to use, there are ways to calculate decision indicators. For example, with the smoothness, if you want to estimate the smoothness, you can use functions from the smoothness estimator namespace, or there are functions that need to, or like decision strategies that need you to predict the error. You can use a particular function there. So these functionalities here on the slide work with either serial and parallel applications. And how to use it in a serial context is now shown in step 27. So we updated the step 27 that it uses all of the functionalities described things that you need to consider if you want to apply it in parallel context. So one of the things you need to consider is load balancing. So in deal.II, in the deal.II approach of parallelization, we partition our domain into smaller subdomains, and each subdomain will be assigned to a certain MPI rank, for example. And to do that efficiently, you need to balance the workload across all of the subdomains. And typically on each cell, the workload is proportional to the number of degrees of freedom that is assigned to it. And that's the tricky part in HP adaptation. In the non-HP case, each cell has the same amount of degrees of freedom assigned, so you only have to balance the number of the number of cells that are living on each subdomain. In the HP context, this is no longer the case. Since you have different finite elements assigned to certain cells, you have also different number of degrees of freedom and a different amount of work assigned to each cell. So what you need is some kind of weight repartitioning for load balancing. And you basically assign a weight which is proportional to the number of degrees of freedom on each cell, and then you try to balance that across all processes. And we have a class that's called parallel cell weights that gives you a convenient way to do that. And just to make my point, you will see in this illustration the first 4 Lagrange elements, which have different kind of nodes, or rather different kind of degrees of freedom assigned to each of them. Okay, so that's one thing you need to consider. The other thing is that you need to pick an efficient solver. So if you use high order finite elements and build a system matrix out of it, you will have many non-zero entries for these kind of elements. And if you use hp-FEM in that sense, the number of non-zero entries varies per row. So you will get some kind of irregular matrix out of it. And from our experience with handling these kind of methods, pure algebraic multigrid methods, they kind of struggle with these kind of matrices. And you see that if you apply to an iterative solver to it, you'll see that the number of iterations will explode the more fragmented your matrix becomes. So we propose an alternative for that, which are geometric multigrid methods, or to be more precise, a hybrid GMG approach, which basically combines P multigrid, H multigrid methods, and then uses an algebraic multigrid method to solve the coarse mesh. But I will describe that in the following slide in a small illustration. This kind of hybrid GMG approach is possible with the new global costing algorithms that Martin and Peter talked about in the earlier presentation. And we'll make use of this MG transfer global costing class in that sense. So as an illustration how you need to imagine this GMG algorithm. So suppose you will start with an HP adapted mesh, which is here depicted on the topmost level. And you want to build up a hierarchy of meshes until you get a coarse mesh. And you do it in a way that you first restrict, so you don't touch the mesh discretization in that sense. You will try to reduce the polynomial degrees on your mesh so far that you only have linear elements left. So this is basically the first step that you do in building the hierarchy of meshes, so that you will end up with a middle layer here where you would only have the H adaptive discretization left, but all of the elements will have the same polynomial degree, preferably linear. And then the remaining levels of your triangulation will be just a regular GMG approach where you build a coarse mesh, where you end up with a coarse mesh in the end. With the coarse mesh representation. Then you solve it, solve the equation system on the coarsest level, and you basically rewind or recover first the H adaptive representation of your mesh, and then recover the correct representation of the mesh with the right polynomial degree assigned. So that's how this hybrid GMG approach works. And last but not least, just want to give like one little slide about the MatrixFree approach. I mean, if you want to apply these kind of methods in serious HPC applications, you will notice that memory bandwidth is the bottleneck, and one way to get rid of that is to avoid storing system matrices at all. So you can use the MatrixFree framework. And this hybrid-GMG method basically allows us to use MatrixFree methods. And yeah, I would again refer to what Martin and Peter talked about in the previous presentation. Yeah, and these are the three things that you need to consider if you want to use parallel HP efficiently. I want to use the remaining part of the talk to just demonstrate these kind of methods in the context of the new step 75 tutorial. So what are we doing in step 75? So step 75, we like solve a simple Laplace problem, but on an L-shaped domain, which has a reentrant corner at the origin. And for elliptic problems, you will typically get a singularity at the origin. And what we try to do with our HP decision algorithms is we want to use this kind of example as a benchmark, so that our decision algorithm should like H refine near the singularity, and then use P refinement in the regions which are smooth, so in all other regions. And this problem is so simple that we can also come up with an analytic solution to it, and we can use this analytic solution to calculate actual errors and see the error convergence problem. So on the right side illustration, you see the actual solution that we try to, the actual solution to the problem. But I will now try to guide you through the adaptation process if you want to solve that numerically. So in the first cycle, we will start with a uniform mesh distribution, which also where we assign the same finite element on our cells. So on the left, you will always see the polynomial degrees that are assigned to each cell. So we start with quadratic elements, but the darker the color will get, the higher the polynomial degree will be. On the right, you will see the partitioning of the mesh here on 12 MPI ranks, and you will see how the mesh will change over time. And we can, so this is meant as a slideshow, I will just like go through that. So you will see that our algorithm really performs H refinement near the origin and performs P refinement everywhere else. And you'll see also how the repartitioning just the domains that are assigned to each MPI rank, and each subdomain covers like a different area of the domain now, but essentially the number of degrees of freedom on each of these subdomains is similar. So just to make my point that we really do H refinement near the center, if we check one slide left that basically zooms into that section here, and you really see that we really just do H refinement near the origin and nowhere else. So that's good. So I have two slides left, which basically show the features of our HP implementation. Actually, these graphs have not been done with step 75 itself, but the side project that I used for my dissertation. But essentially, the problem is the same. We just do more cycles in the refinement, and the problem in general is a bit bigger. So what you see here is the error performance of different algorithms. You will see in a double logarithmic plot the number of degrees of freedom on the x-axis over the H1 error on the y-axis, and we compare here different HP strategies with a pure H strategy, and each of these dots represents one cycle in the consecutive refinement. program. So what you see here essentially is that all of the strategies manage to get the same magnitude of error in the end, but the HP strategies here need a factor of 100 less degrees of freedom to achieve that. For this particular example, I need to add, if you apply this kind of method to different problems, this might change. Okay, and then got one slide left that demonstrates strong scaling. So this is again a double logarithmic plot of the number of MPI processes that we assign to a problem of a fixed size. And on the y-axis, you see the wall time in seconds, and each of these plots represent different parts of the program. And you see that everything scales pretty well until that green barrier, which after which the number of degrees of freedom per process is lower than 100,000. Yeah. And basically the problem is too small and the MPI overhead is too large after that stage. So you see these curves kinking basically. Yeah. And that's what I want to talk about, the current state of the HP framework. So this particular strong scaling example has been done with the AMG solver. I had some trouble making it to get the GMG approach work on large scale applications, but this seems to be like a minor bug, and it might be fixed in the next few weeks. Yeah, and I also need to tell you that we applied this kind of method only to academic problems right now. So like basic Laplace problem on an L-shaped domain. So this algorithm yet needs to prove itself on other applications as well. For example, fluid applications and yeah, other applications as well. So yeah, thank you for your attention.
Okay, perfect timing. Well done. You caught up all of the time that all of the previous speakers, myself included, squandered. So we have a minute for questions or two, and then we have a break. Anybody want to ask Marc any questions?
Maybe if nobody else does, then I do.
Go for it.
How about kind of, is this the scaling plot that you're showing here, Marc? Is this the single L here, or what kind of application is it here in this particular picture?
That's the single L, yeah.
Would you expect the scaling? I'm just curious. Would you expect the scaling if you have, say, 100 of these L's instead of a single one, so you don't refine that much, but you have many more of these singularities in the domain? Would you expect any difference in the scaling? I'm just curious. I don't.
I'm not sure. I haven't thought about this yet. I mean, we could probably also apply the geometry that we used for step 27, for example, where we have.
Yeah, we already have a few of those. I mean, I'm just curious because I'm wondering, because if you have refining very much, then it, well, of course, now this is strong scaling, but I guess if it's very fine, the mesh, I mean, you might have different effects than if you have just repeated the structure many times, but I don't know. I mean, it's curious anyway. I'm not criticizing, it's just my curiosity.
Yeah, I mean, that's just for the L example. I'm not sure how it will behave on different domains, but one of the things we what I'm working on recently is to try to use different domains with reentrant corners. For example, this T-pipe example, also in a different context of like fluid simulations. So I think this would be a better benchmark than just this L domain and the Laplace equation. And maybe when I got the results of that, we could discuss strong scaling results in that regard.
Definitely.
Yeah.
Thanks.
Yeah.
Thank you.
But again, this is just a very simple example, very simple benchmark. Yeah.
Okay. Thank you.
Yeah.
Okay. So the schedule for Sada, we have another question.
Yeah. Just quickly. Do you have any experience with more complex finite element systems where you don't have like just a single finite element, but say for you mentioned fluid flow, where you would have different finite elements from velocity and pressure, and maybe a stability condition between the two, that the polynomial degree has to be something. Is that realistic?
Again, I have no experience with that yet. We will need to see what the future will bring us, if this will be of any issue then. So this example just uses Lagrange elements from order 2 until order 6 or 7, I guess. So I'm really curious, and I hope that things will like turn out easily, but experience tells me that this will not be the case, and we probably need to think about more complicated solutions.
Mm-hmm. Yeah, I know. I mean, it's not that I expect this, but I would be curious to see something like step 31, 32, and
I mean,
see what happens.
This will be the next steps to actually prove that this kind of algorithm is usable in other contexts.
Mm-hmm. Anyway, pretty cool work. Thank you.
Yeah.